Hey, welcome back. Let's revisit the network delay time. So we just talked about it with Dijkstra. So let's try to revisit the problem and try to solve this with a different approach. So let's read the question one more time, just in case that you didn't watch the previous video. You are given a network of n nodes and labeled from 1 all the way to n. You are also given the times, a list of the travel times as a directed edges. Times I has three different values, u, v, and w. And u is the source node and v is the target node, and w is the time that takes for the signal to travel from source to target. So we will send a signal from a given node, k, return the time it takes for all the n nodes to receive the signal. If it's impossible for all the nodes to receive the signal, return -1. That's the case is that you have isolated components. So you are not gonna disseminate your signal to all the other nodes. In other cases, if it's a connected components, you will be able to send your signal to all the nodes, and you're gonna return the maximum path. So, for example, this is the furthest path, and by the time you disseminate your signal all the way to here, and it's gonna take 2, and this is the longest path we have, so that's the value we're gonna return. So you wanna make sure all the other nodes will receive your signal, and that's the problem we'll be asking. And you wanna find the minimum distance you have. So you're on the go into the cycle. But in this case, I don't think there's a cycle, and especially there's no negative cycle, and that's why we can use Dijkstra. But what if there's a negative cycle, and is there any way we can tackle this? And that's the reason when I talk about the second approach, which is the Bellman-Ford. So Bellman-Ford is a variation with DP. So it's more like a DP approach for looking for the shortest distance. So it has a worse, n square time complexity, and that's kind of like really bad compared to Dijkstra. But the benefits from this is when we see the problem with the negative cycle and we need to use Bellman-Ford, and Dijkstra is not gonna solve that. So that's why we're gonna talk about Bellman-Ford in this video. Bellman-Ford is basically a variation with DP. So it's more like a DP approach to solve the short distance. So all we do is like looping through all the node twice. We're gonna loop through all the node twice, and every single time, if we are seeing the shorter distance in the newest layer, we just update it. So that's how we solve it. The algorithm is pretty self-explanatory. So let me just write the code along the way. So I'm gonna explain this along the way. So we are gonna find the shortest distance. So that's why we're gonna initialize this as the maximum value, and we initialize this in SDP, and we're gonna use bottom up in this case. And so k minus 1, and the reason is that we're gonna go from 0 all the way to the length of the node, but the node is given with a decrement, I think. Like, for example, that the node will be 1 all the way to n, but we're gonna shift it 1 to the left to match with our DP cache. So that's why we're gonna -1 from here. So all the values we're gonna -1 just to match our DP cache. But we can do this as well, 2 + 1 right here. It depends on your preference. And then we're gonna loop through the entire node, and we're gonna loop through all the node, and we're gonna loop through the node again from the times. Okay, so we have 2 loops, and then we're gonna track, hey, if the DPU, that's our source node, and plus the W. Oh, we don't have the decrement, the weight. The weight doesn't represent the position for the node, so that's why we just leave it there. And less than the DP for V. So if we can find a path, we can find an edge, adding to this guy, adding to the source node, because we are going from the U to V. So if we go from U to V and adding this edge will make this current node smaller, we just do that. So we just take the new node because we can update it, and that's how we do. And very simple cache. And we have to check the event. So we literally are done. So the only thing we have to check is that for all the DP array, if the max value is less than float infinite, is less than our initialized value, that means like we already updated the value, so we can just directly return the value. Otherwise, we return -1. If you compare the time complexity, it'll be a little bit worse. So when we use Dijkstra, it's like 500 milliseconds, but now it's like 1,000, so it's double. But the time complexity is almost double as well. Yeah, that's how we solve this problem by using Bellman-Ford. I'm thinking about if I should cover for Warshauer-Floyd algorithm. That's for like all pair shortest path, but it seems like this is a one-to-one pair, and we are just looking for one fixed node to other nodes. So it's more like use bazooka to hit a mosquito, so it doesn't worth the try. So anyways, like I'm gonna stop right here. So Warshauer-Floyd algorithm is pretty similar to Bellman-Ford as well, and all it does is that it has one more layer and to calculate all the intermediate steps as well. Maybe in the future I'll cover that. Okay, sounds great. So I'll see you guys in the next video.